Okay, so when we had product rule, it was u times v. We take the derivative. There were different ways you could do this because multiplication is commutative and the addition is commutative. So you may have seen different versions of the way this is written, but we would all agree that with product rule, you do the derivative of one of them and leave the other one alone, and then you add to that the opposite, right? Derivative of that other one and then leave the other one alone, right? That was product rule. So if we take this expression right here and we integrate both sides, we take the antiderivative of both sides. If you take the antiderivative of the derivative, it should cancel out, right? And just leave this thing unchanged. And then over here, it doesn't work that way because the derivative is only on one of the two things. Yes? So what we get is this. The left side here became just u times v. The right side became integral of v, derivative of u, plus integral u, derivative of v. And if we move the one, this, let's say, move this integral, the v u prime, to this side, and then just change the order of things, you get this formula right here. It is the integral of u times the derivative of v is equal to u times v minus the integral of v times the derivative of u. And a way to try and remember this, the way it was taught to me, was the formula is ultraviolet minus voodoo. So you have ultraviolet minus vu, and then u prime is derivative of u, so du, do, voodoo, voodoo. Got it? Ultraviolet minus voodoo. That's a way you can remember it. It always stuck in my mind. Maybe it'll stick in yours. Okay, that's the formula for integration by parts, but let's talk about why it's valuable, why we use it. Because look, you start with an integral, right? And your new problem still has an integral in it. So you haven't really solved the integral, you've just created a different one, haven't you? So what is the meaning of this? Well, the way, again, that I learned it and the way that I want you to understand it is the integration by parts is a transferring of the derivative. It's a transferring of the derivative. Look back up at this formula. On this one on the left side, u is just u, right? V has a derivative on it. On the other integral, the derivative is gone now, right? It's been taken off, and now the derivative is on the u. We have transferred the derivative from v to u here. See it? So if we are presented with an integral, and we want to try and use integration by parts, if we're presented with an integral, we try and identify two pieces within the integrand. The integrand's the thing inside, right? Two things. We have to identify something which we're going to call u. And that u is just some function that hopefully we know the derivative of. So maybe sine x, because the derivative of that would be cosine, right? And then we have to, in the integrand, there should be something that we look at, which we will call v prime, but we need to make sure that we know what its antiderivative is. So something like 2x, because what would be the antiderivative of 2x? X squared. Once you identify those two pieces, then we rewrite the integral using the integration by parts formula, and we transfer the derivative. And things should work out, hopefully, better for us. All right? These are all the steps. It's example time, and each one of these examples I will illustrate what's happening. All right? There's a couple of, every one of these examples has been chosen specifically to show you some different characteristics of integration by parts. So we'll start with example A. Example A. I'd like for us to find the integral x, find the antiderivative x sine 10x dx. And let's really kind of take our time through here, all right? is this just basic power rule? The first thing we ever learned taking antiderivatives. Well, I have x to a power, right? But I have it attached to sine through multiplication. So I can't, remember, big no-no, you can't split this into two separate things because it's a product. Can't do that. So I can't be thinking as simple as just the power rule. Okay, what came after power rule? Substitution. All right, well, do you see something and its derivative? Okay, 10x. What's its derivative? 10 dx. Now I have dx, I agree. I can get rid of the 10, I'm not worried about that. So I have sine, I have, this will become a u, right? This would become what? 1/10 du, right? But I don't have this x, do I? Do I? No. Well, I do though, look. X is here, isn't it? Could I divide both sides by 10? It's an equation, right? I mean, it's a true equation. You could. Now, don't write this down. Please don't write this down because this is going to lead us nowhere. But I just want you to see, I could go 1/10 du is dx. I could take this equation and say 1/10 u is x. Agreed? Now let's rewrite the problem. This became integral. The x became what? 1/10 u. This was sine what? U. And dx became 1/10 du. The 1/10 and 1/10 could come out as a 1/100th, right? So I'd have 1/100th integral u sine u du. And that's pretty much the same integral I just had. I had an x in front, right? I had sine, and then here I had 10x. Well, that's a little better, isn't it? But I have not eliminated that u out front. That x out front still here. The variable still appears. Do y'all see that? So that substitution doesn't look like it's going to work. Perhaps there was a different one. I don't know why my screen is shaking. It's kind of weird. So it's just not happening. But now I hate to erase things. Let me do this instead. Now we have this new technique called integration by parts, where perhaps what we can do is use it, right? So that's no go. So the idea of integration by parts is to try and look at our integral and look at it as a u and then the derivative of something. So notice there's multiplication between these, right? So of all these pieces here, one of them I want to call u, and one of them I want to call the derivative of v. Keeping in mind the whole time that when I do this formula, ultraviolet minus voodoo, I'm going to transfer the derivative from the v to the u. So whatever I call u here is going to become its derivative in the new one. And whatever I call v prime over here, the antiderivative will appear here. So, do y'all see two things being multiplied here? Yes? An x times a sine 10x? So I could choose either one to be u, couldn't I? And then the other one by default would have to be v prime? But does it matter? Like, do you think it matters which one you choose? Absolutely matters. And think about what we're trying to do. Look at this new integral over here. Can anyone tell me what I should choose for u and why I should choose it for u? The x? Why? You're saying the x, I'm going to let that be my u, and then let this whole thing be my v prime? Actually, my v prime will include the dx. You're suggesting that. Why, though? Perfect. Exactly. Look at my new integral over here. My new integral is going to have u prime in it, right? If I call x u, what's u prime? What's the derivative of x? 1. And doesn't that make it go away, essentially? Yes. But if I'm going to do that, I've got to be able to, the other part right here, I've got to be able to turn it into v, which means I've got to be able to find the antiderivative of it. So are you going to be able to handle the antiderivative of sine 10x? Yes. Right? It'll be negative 1/10 cosine 10x plus c, right? So do you see all this kind of unfolding in front of us? All right. Now, just to show you, if I would have done it the other way around, v prime, and then this would have been u, you could argue that, look, I can take the derivative of u, right? I can do that. It would be what? 1/10 cosine, or 10 cosine, whatever, right? And then you could take the antiderivative of x. The antiderivative of x would be what? 1/2 x squared. But now your new integral has 1/2 x squared in it and cosine, right? Which means it's more complicated than it started with, right? It has x squared now instead of x. So you don't want to just blindly swing at this. You want to think about what you're choosing for u in v prime, and that will dictate how the problem's going to work for you. All right? So here's how I write things. Everyone has different notation. Different instructors do it different ways. I've just always done it this way. I start with the table. I like to put u, du. I like to put v, dv. You can use, instead of du, if you want to use u prime, you can, or v prime here. All right, so what did we choose? What did we choose for u? We said x. Okay, I'm going to put that here. And then we chose the other piece to be v prime, and that was the sine 10x, and we will include the dx. So we have accounted for the entire integrand. Everything is accounted for here, right? Now what I'm going to do first is I'm going to come down the left side and just differentiate, right? Take derivative of u, and it's 1. Now, because it's x, I'm actually going to put 1 dx. Is that all right? Just like we did before when we were doing substitution, whatever we called u, this dx would always pop out. Same thing. Now, to go from dv up to v, what operation do I have to do? Integration, right? Coming down was differentiation. Going up this table is integration. So going up from here to here, I'm going to put an integral sign there, okay? Going down from here to here is the, okay, du, right? I'm taking a derivative coming down. There I'm integrating. So what did we say the antiderivative of this was? Negative 1/10 cosine 10x, right? Now, don't worry about your plus c yet, all right? We'll get that at the very end of the problem. Any questions on this? Do you see why I showed you this just a second ago? Like if you have a linear expression inside, I just did that so we wouldn't have to worry about that when we got here. All right, let's put the integration by parts together now. This integral should become, according to this formula, ultraviolet, u times v. Here's u, here's v, right? Just multiply these two things together. X times this. Wouldn't that just give me negative 1/10 x cosine 10x? Yes. And then I have minus integral of v u prime, or v du, which would be this one, v, times this one, du. So just multiply these across. isn't that just going to be negative 1/10 cosine 10x times what? 1 dx. So just, I'll put 1 dx even though I don't really need the 1. Which is negative 1/10 x cosine 10x. I'm just going to pull out the 1/10, the negative 1/10. And when I have negative and negative, this should become plus, right? So plus integral, plus 1/10, integral cosine 10x dx. What's the antiderivative of cosine 10x? 1 over 10 sine 10x. And that's going to hit the 1 over 10 that's already there, right? So 1 over 100. Negative 1/10 x cosine 10x plus 1 over 100 sine 10x plus c. That's it. I can't go any lower on this page. How could you check your work? Take the derivative of this. That would become somewhat troublesome because you've got product rule here, right? So you'd have to do product rule on that and then get that over there, and trust me, it'll work, all right? But we're not going to check it. So it seems as not a very complicated integrand, right? X sine 10x, all right. Look at the antiderivative. That's something you would never be able to just look at and get, right? It's just not happening. So that's the power of integration by parts. Example B. Antiderivative arc sine of pi x dx. The example we just did was an example of a basic integration by parts. You pick a u, you pick what's v prime, you make your table, you grind it out, you're done. This is an example of an integration by parts that's not so obvious. So right now, why is it that this is not an obvious integration by parts? It's only one part, right? I mean, you look at this, you only see really one thing, right? Arc sine of pi x. Do you know what the antiderivative of arc sine is? It's not on any formula sheet. Now, you know what the derivative of it is, right? Derivative of arc sine of something is 1 over square root of 1 minus that something squared or something like that, right? But you don't know what the antiderivative is. Are we all kind of on the same page that it's not obvious that this is integration by parts? Okay, but I'm going to take a swing at it with integration by parts. I have to pick something to be u, and I have to pick something to be the derivative of v. I might try this and may not work, and I might have to make a new table and try something else. Well, there are actually two parts up here. There's the arc sine of pi x, and the other part is just the dx, just dx itself. Now, this is going, if you look at it this way, this is going to force your hand, because I cannot take the derivative of dx unless I want to get the second derivative involved, which I don't. So that forces me to choose this one as the one that I'm going to wind up taking the derivative of. So it forces me to choose this one to be u, which means this one needs to be v prime. Let's see if that creates any issues. U is equal to arc sine of pi x. In the back of my mind, I'm thinking, can I take the derivative of this? Yes. And then the dv is going to become the dx. And then I'm thinking, can I take the antiderivative of dx? What's the antiderivative of dx? It's just x, right? Because that's like 1. Isn't that 1 dx? The antiderivative of 1 is x. So I can go up. I'll do the v first because I'm right there. That's x. And then coming down derivative-wise on this side, I go on my table if I don't remember it. It's 1 over the square root of 1 minus whatever was there squared, right? So pi squared x squared, you have to square both the pi and the x, right? So pi squared x squared. Am I done? Am I done with this? Before dx, chain rule, I had to go and take derivative of what was in there. Pi. Pi, right? Because the derivative of pi x is pi. So why don't I throw that pi up on top? Instead of a 1 on top, I'll put the dx out here. So the derivative of arc sine of pi x is 1 over the square root of 1 minus pi x squared times pi dx. And that's this. Questions? This equals then, by the integration by parts formula, ultraviolet. So here's ultraviolet right across here. So x arc sine pi x minus integral of voodoo. Voodoo is this way. So what happens when I multiply this x times this fraction? It appears on the top, doesn't it? So I have integral pi x over square root of 1 minus pi squared x squared dx. The whole idea behind integration by parts is to make the integral easier. Is that integral easier? You can use substitution. How? Choose u as this whole thing, you're saying? And then what happens if I take derivative of that? So you're just off by a constant. So this will actually work. That integral is going to go by substitution, which is what we did last class and which everyone mastered on their homework, right? You see what I'm saying? Like how this builds on itself very quickly? That problem now would be considered to be a fairly routine substitution problem at this point. But I'll continue. I'm going to take it all the way. So what I'd like to do now is take my little zoom in glasses here and just look at this integral. And I'll come back and put the answer in at the end. So I'm going to just scroll down, do some work down here. I've got integral pi x over square root 1 minus, it was pi squared x squared dx. I've been told to make a substitution of the entire bottom, 1 minus pi squared x squared. I can call it u, right? A u substitution. But I used u up here. So just to make sure we don't mix variables up, I'm going to use something other than u. W is fine. So I'm going to make a w substitution instead of a u substitution. W is going to be the entire denominator, or what's underneath that root. The derivative of w will be, the derivative of 1 is 0. Negative pi squared is a constant. The derivative of x squared is 2x. So the 2 is just going to come out in front of that. Negative 2 pi squared x dx. Questions on that? I'm here for you. You just got to ask. No, because it's a constant, right? Pi or pi squared, they're both just numbers, so we just leave it alone. Now, we need to make things match, though. That's where I'm going next. I'm going to replace this whole thing, right? That's going to be my u, right? And then the pi x dx, I don't have pi x dx over here, do I? But I'm going to make it a pi x dx. I'm going to take the negative 2 out of here. I'm going to take one of the pi's out of here. How do I do that? Divide both sides by negative 2 and pi. So I will have 1 over negative 2 pi dw equals, when I divided this side over here by negative 2 pi, it left me with exactly pi x dx. That's the exact match I'm wanting. So my pi x dx will be replaced with the 1 over negative 2 pi dw. Questions now? What's my new integral? You want that constant out? I'm going to take that constant out. Okay. What's still left here? 1 over square root of u, right? 1 over the square root of u, but that's really what? U to the what? That's u to the negative 1/2. 1 over the square root of u. Yes, thank you. See, that's right. Thank you, sir. That's one. This right here should have been 1 over the square root of w, which you bring up, make it a negative exponent. And then what's out here? dw. That's it. What is the antiderivative of w to the negative 1/2? So you've got 1/2. So it'll be 2w to the 1/2 plus a constant. Notice that when I'm doing power rule now, I'm not doing the 1 over 1/2. Right? When we add 1 to negative 1/2, we get 1/2. I'm not showing the 1 over 1/2 anymore. I'm reciprocating it when I'm writing it for the first time. And now these 2's cancel. And so we get negative 1 over pi square root of w. What's w, though? 1 minus pi squared x squared plus my constant. Yes? Box it up? Nope. That's only the last part of this. Remember, there was more. Right? Don't forget about that. So now I'm ready to come back up here and put my final answer. My final answer is x arc sine of pi x minus, hey, but look, this was negative, wasn't it? So it's going to be plus 1 over pi square root 1 minus pi squared x squared plus a constant. That I will box up. Wow, how innocent this thing looked, right? Arc sine, antiderivative, no big deal. It took a little work, right? I'm sure all of you have been made aware of the Wolfram alpha, right? And that you can go here and go integrate arc sine of pi times x. That's what we were trying to do? That's it right there? That what we got? Everyone's like, what? Wolfram what? Wolf what? Howling and shit. You're all excited about it? Look, this is a very powerful tool. In fact, I think the future of a class like this is where we do very little integration by hand, almost do it exclusively with a computer, and we actually get into more of applied math, applying it to real world situations. This is the way I'm showing you calculus is the way it's been taught for ever, okay? Ever. The technology has come so far in such a short period of time. When I first started using Mathematica, which did I tell you I use Mathematica, and that's what, like, all my notes come from Mathematica. Mathematica is the actual kernel, the brains behind this website. And when I first started using Mathematica, it could not do this. It's really come far. Here's the danger, though, and this is what we call the black box. The black box in engineering and things, computer science. You're an engineer. You want to build a bridge, so you're trying to, you set up these things, and you're trying to figure out the strengths of materials, things like that. And you got a buddy who's like, yeah, well, we just, we throw it into this program. Just put in your things here, and it'll spit out, and that's your tolerance that you need. Blah blah blah. If no one in that company knows the algorithm being used, it's just a black box. It's whatever comes in, you're trusting that answer out, right? And if nobody can figure out how that algorithm is being generated, the true mathematics behind it, then at some point we lose the mathematics completely, and nobody really has a good grasp of the theory anymore, and so we don't know what we're getting out, if it's junk or not. So there's this balance, I think, that has to be made. We're not there yet, unfortunately. I think there will be one day where everybody would walk in here with some sort of tablet. We would all have internet connection. We would all be able to get to Wolfram Alpha, and we would just say, okay, here's a physical problem. We set it all up, and we get to an integral, now integrate it, right? And not integration by part. You understand what I'm saying, right? We're not there yet. So maybe in like 10 years, when you're talking to your friends about their kids in college, and you're like, well, we didn't have that. We had to do everything by hand, man. And you can say all that stuff. But unfortunately, you can't right now. So this is a great website to come as a reference, all right? There's always a danger with Wolfram Alpha because Wolfram Alpha is smarter than us, okay? In other words, it knows functions that you don't know and you will never know, like phi functions and weird error functions. So it'll spit back to you something that you're like, I'm trying to get that answer, I can't. And your answer's correct, but they are using some other function to represent your answer. I'll give you an example. Classic integral. This is one of the most classic integrals out there. It's the antiderivative of e to the x squared dx. That integral, as innocent as it may look, cannot be integrated in a closed form. In other words, there is no technique that we have that you can find the antiderivative of this. Integration by parts doesn't work, nothing, all right? However, Wolfram Alpha says 1/2 square root of pi ERFI x constant. Now, what is ERFI? Oh, over here. ERFI is the imaginary error function. So it's talking about something that you have no idea, you will never see in your life unless you're a math major and you go to do a lot of math. So you may be sitting there going, I'm trying to get this thing and I have no idea what the hell this is. Well, that's because you're not going to. All right? So just be careful if you're checking problems, homework. That's all I'm trying to get you to see. Just be careful checking here. Didn't someone already ask me that this semester? Right? The hyperbolic or something? It was that one, it was natural log x. Yep. It simplified the answer. It took it all the way. It simplified it, and it came out to be a polynomial or something, right? So just be careful with this. Now, do you remember me talking? Did I talk about the two fathers of calculus, Newton and Leibniz? Okay. I said Newton's was more powerful. See, what's going to happen, as we will see later on this semester, is that the way that Newton would attack this problem is that he would turn it into his power series, which is this. And then he would integrate each one of those term by term. And this series of power functions goes on forever. So I can't tell you the exact antiderivative of this, but what I can do is I can come up with a function that's really close to the antiderivative of this. And then you say, how close? And I say, how close do you want me to be? And then you know, you say, I want to be within 1/1,000,000,000th. And then I have a way of knowing, computing how many of those terms I need to calculate them. If you say, I need you to, your tolerance has to be within 1/1,000,000,000th of the true result, then I may need 100 of those terms to do it, but I can do it. And I can go as tolerant as you want me to go. So Newton had a way around functions that we couldn't integrate in a closed form. Shall we do another one? This will be our last one for today. And then we'll come back and we'll do more next time. Now I've switched up the variable here on you. I'm using t instead of x. How do you know t is my variable, not beta? The dt is telling me what my variable is. And then what's beta? Beta is a constant. We assume it's a constant. There's somewhere in this book where they tell you, like, anytime you see like A, B, C, D, or alpha, beta, to assume that they're numbers, constants, unless otherwise specified. This looks a lot like the one we just did a little while ago where it was x sine 10x, doesn't it? X sine 10x. Except instead of having the x, we have t squared. Let's just see what happens. Integration by parts is the technique I'm going to attempt. U, du, dv, v. I am well aware that there are some people who have taken Cal 2 before in here, and people who have seen Cal 2 previous in their life, and may know of a thing called the Tabular Method, where you do things here, here, and then you go diagonally. Anyone ever seen that before? Okay, if I'm aware of that. I don't teach it. I'm not a big fan of it. But if you use that and you want to, go for it. All right? Any ideas on what we should choose for you, maybe? Cosine? Okay. If we do cosine for u, the derivative we know, right? Then what's going to be your dv if you use cosine for u? T squared. Then what's going to happen when I go up with t squared? One third. It's 1/3, right? T cubed. Didn't that just get worse? See what I'm saying? So maybe the other way. If u is t squared, what's the derivative of t squared? 2t. So it got better, right? And then you'll have to go up with the cosine. The antiderivative of cosine is sine, right? So let's just try that. U is going to be my t squared, and the derivative of that is 2t dt, right? My dv was forced to be the cosine beta t dt. And when I go up with this, what happens? 1 over beta sine beta t. Question? Ultraviolet minus voodoo? So this is, ultraviolet would be 1 over beta t squared sine beta t. That's ultraviolet. It's this part. Minus voodoo, which is this. Voodoo, I multiply these two together, right? So I have, how about 2 over beta times t times sine beta t dt. Would anybody mind if I pulled a 2 over beta out right now? Out of the integral? Does anybody have a question as to what the hell I just did, pulling the 2 over beta out? Doesn't the NFL season start tonight? It does, right? Packers. Is Rodgers playing? He's healthy? Okay. Is that a Cowboys shirt you have on over there? I'll act like I don't see that. Kidding. Good luck. I hope y'all have a good season. Any questions on this? Did we get anywhere? Are you, bless you, are you going to be able to integrate this? How? We're going to do integration by parts again. Because what happened was, in the first application of integration by parts, we went from a t squared down to a t. Right? And if we do it again, we're going to be able to take that t down to a 1. So we apply it 2 times. Big deal. So what I'll do is I'll box up just this integral. I'm going to take that to the side here and do some work and come back and put my answer in there when I'm done. So what I'm working on now is integral. Notice I left the 2 over beta out. I'll just remember that it's there later. I've got t sine beta t dt. I'm going integration by parts again. Bless you. I'm gonna use u and v again, as long as we just understand that it's a new integration by parts. Don't confuse it with the u and v from up there. U here, du, dv, v. What am I choosing for u? T. And then my dv is the other part, which was sine beta t dt. The derivative of u, dt, antiderivative of sine beta t. Negative 1 over beta cosine beta t. Look at voodoo. Voodoo only has cosine, doesn't it? And I'll be able to integrate that when it's time. So just this integral becomes ultraviolet, negative 1 over beta t cosine beta t, minus voodoo. There's voodoo. But what's voodoo? Constant do I have with voodoo? When I put voodoo here, what's the constant? Negative 1 over beta? Can I pull that out of the integral? And when I put it together with this negative, it becomes plus. So I'm going to have 1 plus 1 over beta, and then inside that integral is what? Cosine beta t dt. And this integral should be straightforward. Antiderivative cosine, it's going to be sine, but 1 over beta sine, right? Beta t. So I've got negative 1 over beta t cosine beta t plus 1 over beta times 1 over beta again sine beta t, and I'll have plus some constant. Right, this antiderivative of just this part right here became this 1 over beta sine beta t plus c. Now I've got to take that, right, and I've got to put it all together back with this answer, right? I think I'll do that, and then we'll get out of here. So this is equal to, I'm going to go to a smaller pen here, 1 over beta t squared sine beta t. Now, I had what out here? Negative 2 over beta. And that's got to distribute. You know what? I'm not going to be able to fit all that on there. I'll do something instead. Just grab all this crap and take it to another page. Did I cut it? And then this one right here. All right? Here we go. So this becomes 1 over beta t squared sine beta t minus 2 over beta times everything I just got, which was negative 1 over beta t cosine beta t minus 1 over beta, so 1 over beta squared sine beta t plus c, and I'm just going to throw a c at the very end of this problem. Is that okay? Then distribute, and we're done. So 1 over beta t squared sine beta t plus 2 over beta squared t cosine beta t plus 2 over beta cubed sine beta t plus a constant of integration. This was an example of what we call repeated integration by parts, right? Because we used it more than one time in the problem. I've seen it used 3-4 times before in a problem. It can happen. I'll put that back up in a second. I'm going to see what Wolfram alpha does with that. The original problem was t squared times cosine b, I'm going to say b times t. And that was it, right? Let's see what it does. So that doesn't look like ours, does it? Oh yeah, no, they distribute, if you distribute this through, I believe it works out and matches up. I believe you can see step-by-step solution of how to do it, like they show you the technique, but guess what? You got to pay for it. Oh wait, why is it letting me? Oh yeah, step-by-step solutions, they'll show you how to do it, but you got to start paying for it. Or you, yeah, all right. So let's just put this in perspective. I know I'm 1 minute over, but let's just put today in perspective. Quiz problem. the last problem of class. You see what I'm saying by we have to keep up with the pace of the course. You have to, or you're just going to fall to the side. And yeah, I'm put it back up. Good luck. Have a good weekend. Watch some football and do calculus. Homework for this section. You can't do them all yet because I haven't shown you all of them yet, but page 316, you can at least get started with 1 through 12. I think I did, no, I did 12? I did 12, yes. 1 through 12. Start with that. You should, I should point out before y'all get too far ahead, because I know some of you like to do other problems in the book. If you do a problem, you see an integral sign on it, and you see numbers like 2 and 3, if I assign a problem that has these numbers on them, right now, ignore the numbers. Just act like it was a normal integral sign, and just do the antiderivative. Have a good weekend.